the software encodes this quantization. So again, let me have this mono track. So last time we talked about the rate, right? The rate is a sampling rate. The standard is 44100, and but also, you can also choose different rates. Okay, and there is something called format. So this is the quantization B depth. So let me create something. So again, like last time, let's generate a tune, a sine tune, okay, of this frequency 660 and amplitude 0.4, and this duration is 0.5 seconds. Okay, generate this and play this sound. Okay, so this is a pure tone, and you can actually zoom in to see, right? This is actually a pure tone, a sine wave, sinusoidal wave, actually, and it's sampled, to these different points, the by sampling rate. So for now, this is sampled at standard sampling rate. We're not going to change it, but we can if we change it to 8,000, like this. So you can see there are the number of points there are different, right? So I change it back to the standard rate. So now we are going to explore this quantization. So here you can see they use 32 bits. So 32 bits is 2 to the power of 32. So this is actually have the finest resolution, right? So you can represent the signal to the best quality with the minimum signal to noise ratio. But we can also use 16 bits is 2 to the power 16, we just calculated, right? Using this. So this is, the 16 bits. So this is the resolution for your 16 bit. So here you can choose different format, like 24 bit. Okay. Do this. 32 bit, 16 bit. But you barely can see any difference here, right? Okay, let me do this again. So because if you change the rates, you can see it immediately, right? It change. So it actually the program works. It's not a problem of my interface or this software. The problem is that why you cannot see any difference here when you choose different bits, because these bits are too fine. Even if we choose the coarse, the most coarse bit here, 16, the resolution is still 0.00001. So for this number, actually you cannot visualize this here, right? Because I think what you can really see here, the largest would be like 0.1, the change. So because this is actually very fine kind of quantization, and our visualization is kind of limited unless we can zoom in, right? On this vertical, if we can zoom in here, I don't know how to do this. Okay, if we can zoom in more and more like this, you can see if we can zoom in more and more, and to certain points, I believe we can visualize this. But for now, you can see it's still too coarse comparing to the quantization rate. Therefore, by visualizing this software, you cannot tell the difference here for this quantization format. But if you listen to the audio, you should be able to discover this subtle difference there. Okay, if you are very sensitive, if you're doing this very fine music production or audio, you are audio expert, or you are dealing with certain audios that's very sensitive to quantization, right? Then you are able to hear this through your ears. So this is quantization, what I want to address here. So now let's continue with our topic on harmonic waves. Okay. So for the harmonic waves, last time actually we tried this in Audacity, right? Let me let me still use this thing, but so last time we actually generated several tracks and we generated different harmonic waves using Audacity. So this is very easy, right? Just one click, just choose the different format. So for example, we choose the sawtooth, and we use the same frequency, same amplitude, same duration. Let's generate. Okay. So if we zoom in, you can see the difference of the waveform. Okay. So this is a sawtooth or a phasor. So yeah, it's basically a ramp line from -1 to 1, and then it drops back to -1 to 1. Okay, so here is like -0.4 because my amplitude is 0.4. So yeah, this is just a ramp line, up and go back and up, go back. And another, okay, let me rename this track to sine. Rename this to sawtooth. Okay, another track. Let's generate triangle. Okay. Generate two triangle. Okay. So the triangle wave, you can see the shape here, right? So it's actually of this triangle shape, right? Up and down, up and down, up and down. And before we hearing this sound, let me generate another one, which is a square. Okay. Generate two. So you can see here actually two versions. We will compare those two versions, the difference later on in more detail, but let's generate a square now. Just pure square. Okay. So you can see this square is just up and it's still like it's a very sharp line here, right? So you have something negative and directly something positive and interchanging with each other, negative, positive. And this is a square wave. So let's maybe hear those sounds. So now I muted every other track. I'm doing solo for the sine wave. Okay. About sawtooth. So it's much more like brighter. If you describe the sound quality, it's brighter, right? It's more like sharp, harsh, I would say. What about triangle? So triangle is better than sawtooth. It's more gentle, but it's not as gentle as the sine tune, right? Well, square. The square is also creating this very sharp, or I would say somehow dissonant sound. Okay, not very pleasant sound. But if we go back to sine wave, triangle, square. Okay, so one question might be like, why we study those harmonic waves? Okay, so one intuition should be So we're talking about oscillations or periodic waves, right? Periodic sound or phenomenon. So talking about periodic, it means, right, something is like repeating itself. So we only talk about so far, like everything we are talking about is about sine, right? Is of this shape, of this sine wave, sine shape. So a question or a natural thing would be like, why we only talk about sine, right? Because if you think about periodic, everything like have the same frequency, right? So everything repeating like this, whatever the shape of the wave, right? As long as it's repeating this part at a certain frequency, it should be considered like periodic signals. So this is why like we are studying different types of signals, because you can see actually all those signals, they are of the same frequencies, right? So everything is of the same frequency, but they are of the different shapes. And we are actually picking up like certain like representative shapes like squares, triangles, sawtooth as a representative of this type of periodic signals. So the way people study those harmonic waves is actually traditionally using additive synthesis. Okay. So if we go to this link, so we can see what people do or how do they describe the properties of those square wave, triangle wave, sawtooth wave, is that they actually decompose those waves into the sum of sine waves. So when they decompose these waves to the sine waves, actually, if you consider the sinusoids, it creates the upper harmonics. Okay, so what is upper harmonics? It means in the square wave here, right, or triangle, whatever wave here, so if you think about this, it doesn't only contain this type of sine wave, okay? It also contains the sine wave. Okay, so this is a sine wave, the sine wave of twice of the frequency, okay, or third of the frequency, or the fourth. Okay, I'm not drawing very well, but these are actually the upper harmonics. So actually they add up those upper harmonics, and they find that when you do this infinitely, or you deploy this limit, okay, so there is actually a limit. So this is limit, right? So from 1 to infinite, if you're doing this limit operation and you adding up all those sine waves, of the harmonics, upper harmonics, you can actually get the exact wave: triangle wave, square wave, and sawtooth wave. So there are different formulas. So for square wave is this formula. For triangle wave, there is a different kind of formula, but the idea is the same. It's only the coefficients are different, but the contents are somehow similar. Okay, so you are just adding those upper harmonics of the sine waves, and then you create those different shapes of waves. So this is actually a very deep and significant idea. Okay, and this is called the Fourier series. Okay, so this is a very like influential. I would say influenced everything, every aspect of signal processing, and basically everything you see now, like about audio processing, and how people, even how they solve the partial differential equations, because actually the sine and cosine waves, the sinusoids, provide a different basis for you to view these functions, right? When you decompose the function into sine and cosine, it provides you a different basis. So we'll get more into this kind of thought, right? This thought later on. It's about the algebra, linear algebra, but it's deeper than how to do the math, right? It's about how you view the world, how you think about a subject. So what I want to show you is that before we talk about those formulas, the most important thing is that you understand the concept. Okay, so the concept is it's called Fourier series. So we'll watch this video together to get a better sense of the Fourier series. Okay. So maybe let me open this here.
Here, we look at the math behind an animation like this one, what's known as a complex Fourier series. Each little vector is rotating at some constant integer frequency, and when you add them together, tip to tail, the final tip draws out some shape over time. By tweaking the initial size and angle of each vector, we can make it draw pretty much anything that we want. And here, you'll see how. Before diving into it all, I want you to take a moment to just linger on how striking this is. This particular animation has 300 rotating arrows in total. Go full screen for this if you can. The intricacy is worth it. Think about this. The action of each individual arrow is perhaps the simplest thing you could imagine, rotation at a steady rate. And yet the collection of all added together is anything but simple, and the mind-boggling complexity is put into an even sharper focus the farther we zoom in, revealing the contributions of the littlest, quickest, and downright frenetic arrows. When you consider the chaotic frenzy that you're looking at, and the clockwork rigidity underlying all the motions, it's bizarre how the swarm acts with a kind of coordination to trace out some very specific shape. And unlike much of the emergent complexity you find elsewhere in nature, this is something that we have the math to describe and to control completely. Just by tuning the starting conditions, nothing more, we can make this swarm conspire in all of the right ways to draw anything that you want, provided that you have enough little arrows. What's even crazier is that the ultimate formula for all of this is incredibly short. Now often, Fourier series are described in terms of something that looks a little different, functions of real numbers being broken down as a sum of sine waves. That turns out to be a special case of this more general rotating vector phenomenon that we'll build up to, but it's where Fourier himself started, and there's good reason for us to start the story there as well. Technically, this is the third video in a series. All of this is incredibly short. That turns out to be...
Okay. So here, it actually shows the animation of summing of those sinusoids. So it's used cosine. So, but cosine and sine is just a difference of phase, right? So summing up those sinusoids, but you can see this minus, plus, and 1/3, 1/5. They are coefficients. So this is a good animation of showing you how do you add up those sinusoids to get a square wave. Okay. So this is the formula for the square wave. How do you get the square wave? So this is the pulse, the square wave here. And this, if you do this limitation, which means you add infinite upper harmonics, you can get a perfect square wave here. Okay. So I think it's worth it to look into this animation, and then you can have a better understanding of what is upper harmonics. How do you do these additive synthesis to get the square waves?
A special case of this more general rotating vector phenomenon that we'll build up to, but it's where Fourier himself started, and there's good reason for us to start the story there as well. Technically, this is the third video in a sequence about the heat equation, what Fourier was working on when he developed his big idea. I would like to teach you about Fourier series in a way that doesn't depend on you coming from those chapters, but if you have at least a high-level idea for the problem from physics which originally motivated this piece of math, it gives some indication for just how unexpectedly far-reaching Fourier series are. All you need to know is that we had a certain equation which tells us how the temperature distribution on a rod would evolve over time. And incidentally, it also describes many other phenomena unrelated to heat. And while it's hard to directly use this equation to figure out what will happen to an arbitrary heat distribution, there's a simple solution if the initial function just happens to look like a cosine wave, with the frequency tuned so that it's flat at each endpoint. Specifically, as you graph what happens over time, these waves simply get scaled down exponentially, with higher frequency waves having a faster exponential decay. The heat equation happens to be what's known in the business as a linear equation, meaning if you know two solutions and you add them up, that sum is a new solution.
Okay, so this linear equation, so when we talk about the wave equation, if you remember the partial differential equations, right? So here they use the heat equation because heat equation is the original PDE that Fourier used, this kind of Fourier series to solve, to give this give the solution for heat equation. But what we concern more in this class is the wave equation, right? Wave equation, if you remember, the formula is U. So we use U is square is equals some constant K times U X, right? So this is our wave equation. So I think if you look at this, the difference is only that. So here is the same, right? It's only that in wave equation we have the second derivative of time, but here heat equation is only like first derivative of time. But despite the difference, okay, there are a lot of difference in terms of solution and whatever. But the one thing in common between this wave equation oh no, you cannot see that, right? But yeah, this is a wave equation. One thing in common would be they are both linear PDEs. Okay, they are all linear solution. Though they are linear equations, so they have linear solutions. What is linear solution means? It means that when you have two solutions here, right? T and T1 and T1 and T2, and when you plus those two solutions together, you get another solution. So this is linear. If you remember, we talked about the superposition, right? Superposition principle for the waves. When you have two waves, when you add them together, they won't interfere with each other. So it is a simple add there, right? So the wave is still, they just add upon each other, and you can decompose them linearly, adding them linearly. And also, when you add two solutions for this equation, you get another solution. Okay. So both the wave equation and heat equations are all linear PDEs. Okay.
You can even scale them each by some constant, which gives you some dials to turn to construct a custom function solving the equation. This is a fairly straightforward property that you can verify for yourself, but it's incredibly important. It means that we can take our infinite family of solutions, these exponentially decaying cosine waves, scale a few of them by some custom constants of our choosing, and combine them to get a solution for a new, tailor-made initial condition, which is some combination of cosine waves. One important thing I'd like you to notice is that when you combine these waves, because the higher frequency ones decay faster, the sum that you construct will tend to smooth out over time as all the high frequency terms quickly go to zero, leaving only the low frequency terms dominating. So in a funny way, all of the complexity in the evolution of this heat distribution which the heat equation implies is captured by this difference in the decay rates for the different pure frequency components. It's at this point that Fourier gains immortality. I think most normal people at this stage would say, well, I can solve the heat equation when the initial distribution just happens to look like a wave, or a sum of waves, but what a shame it is that most real-world distributions don't at all look like that. I mean, for example, let's say you brought together two rods which were each at some uniform temperature, and you wanted to know what happens immediately after they come into contact. To make the number simple, let's say the temperature of the left rod is 1 degree, and the right rod is -1 degree, and that the total length, L, of the combined two rods is 1. What this means is our initial temperature distribution is a step function, which is so obviously different from a sine wave, or the sum of sine waves, don't you think? I mean, it's almost entirely flat, not wavy, and for God's sake, it's even discontinuous. And yet, Fourier thought to ask a question which seems absurd. How do you express this as a sum of sine waves? Even more boldly, how do you express any initial distribution as a sum of sine waves? And it's more constrained than just that. You have to restrict yourself to adding waves which satisfy a certain boundary condition, And as we saw last video,
okay, so we also talk about the boundary condition. We're talking about the standing waves, right? If you remember, okay, let me go back there. So let me remind you what we did before, and then you can have better understanding here why we need upper harmonics. Why it's only the harmonics of integer multiples of the fundamental frequency, right? Why it's not, other types of frequencies there because it has to satisfy this boundary condition. So when we talk about the boundary condition on these standing waves, yeah, right? For standing waves, because now you have these two boundaries, right? Two fixed nodes, which means you can only have this type of wave that are of this form. Okay. So you have this fundamental mode because you have to fit into these boundary conditions. So your two nodes, right, are fixed. This is your boundary, which means you cannot have any other frequencies here. The only frequency you can have for the first 5 modes are like this, and these frequencies are all the integer multiples of this lowest frequency. Okay, so this is why in all those functions here, right, you can have 2 pi 2k minus 1t, right? So you only have these integers like 1t, like 1, 3, 5, 7, right? Where you have those harmonics. So it gives you an explanation like why you only have these modes, right? Well, you have only have those modes because of the boundary conditions.
that means working with these cosine functions whose frequencies are all some whole number multiple of a given base frequency. And by the way, if you were working with some different boundary condition, say that the endpoints have to stay fixed, you'd have a different set of waves at your disposal to piece together. In this case, simply replacing that cosine.
Right, so you can see in this animation, every wave generated here, they all start from 0 and end with 0. Okay, so this is the boundary condition. They have to here. So let me maybe replay this so you can see this animation again from the beginning. So here you can see, right, this wave doesn't really like start from 0. Therefore, this wave cannot really exist in this summation because it doesn't fit the boundary condition. Okay, so later on in that animation, you will see every wave that it was used to create the square wave, they all fit the boundary condition, starting with 0 and ending with 0.
You have to restrict yourself to adding waves which satisfy a certain boundary condition. And as we saw last video, that means working with these cosine functions whose frequencies are all some whole number multiple of a given base frequency.
Okay, sorry. So I think okay, I said something wrong. So here is it's not sine, it's a cosine. So it always starts from the largest amplitude. Okay, so the boundary condition is it is cosine, so it always starts from the largest amplitude, but it's still a kind of boundary condition. Okay, it's just different from sine. But there's still these restrictions to those certain harmonics.
And by the way, if you were working with some different boundary condition, say that the endpoints have to stay fixed, you'd have a different set of waves at your disposal to piece together. In this case, simply replacing that cosine expression with a sine. It's strange how often progress in math looks more like asking a new question rather than simply answering old ones. Fourier really does have a kind of immortality now, with his name essentially synonymous with the idea of breaking down functions and patterns as combinations of simple oscillations. It's really hard to overstate just how important and far-reaching that idea turned out to be, well beyond anything that Fourier himself could have imagined. And yet, the origin of all this is a piece of physics which, at first glance, has nothing to do with frequencies and oscillations. If nothing else, this should give you a hint about the general applicability of Fourier series. Now hang on, I hear some of you saying. None of these sums of sine waves that you're showing are actually the step function. They're all just approximations. And it's true. Any finite sum of sine waves will never be perfectly flat, except for a constant function, nor will it be discontinuous. But Fourier thought more broadly, considering infinite sums. In the case of our step function, it turns out to be equal to this infinite sum, where the coefficients are 1, negative 1/3, plus 1/5, minus 1/7, and so on for all the odd frequencies, and all of it is rescaled by 4 divided by pi. I'll explain where those numbers come from in a moment. Before that, it's worth being clear about what we mean by a phrase like infinite sum, which runs the risk of being a little bit vague. Consider the simpler context of numbers, where you could say, for example, that this infinite sum of fractions equals pi divided by 4. As you keep adding the terms one by one, at all times what you have is rational. It never actually equals the irrational pi divided by 4. But this sequence of partial sums approaches pi over 4, which is to say, the numbers you see, while never equaling pi over 4, get arbitrarily close to that value, and they stay arbitrarily close to that value. That's all a mouthful to say, so instead we abbreviate and just say the infinite sum equals pi over 4. With functions, you're doing the same thing, but with many different values in parallel. Consider a specific input, and the value of all of these scaled cosine functions for that input. If that input is less than 0.5, as you add more and more terms, the sum will approach 1. If that input is greater than 0.5, as you add more and more terms, it would approach negative 1. And at the input 0.5 itself, all of the cosines are 0, so the limit of the partial sums is also 0. And that means that, somewhat awkwardly, for this infinite sum to be strictly true, we do have to prescribe the value of this step function at the point of discontinuity to be 0, sort of halfway along the jump. Analogous to an infinite sum of rational numbers being irrational, the infinite sum of wavy continuous functions can equal, honest to goodness equal, a discontinuous flat function. Getting limits into the game allows for qualitative changes, which finite sums alone never could. There are multiple technical nuances that I'm sweeping under the rug here. Does the fact that we're forced into a certain value for the step function at the point of discontinuity make any difference for?
Okay, so it talks about the limit or approximation. So if you took the calculus, right, in your first year, you should have seen this limit, infinity, this type of concept in your basic math courses. So here, I think what he wants to illustrate is that when he used the example of this equation is that everything on the left-hand side, the 18 terms, they are actually rational numbers, right? They are rational numbers. Maybe some of them are, infinite, but they are rational numbers. But the summation they finally get is pi over 4. So it's the irrational number. So which is like not really like makes sense if you think about in finite terms, right? If you for finite terms, no matter how many rational numbers you add them together, like many numbers, like billions of billion, it will never be a irrational number. It will always be a rational number. So this equal happens only when you take the limit, right? When your eigenterms are infinite, that's where it's possible to get a rational number by pure adding those rational numbers. So the same concept actually applies here, because when you think about this pulse equation or the square waves, right? It's a pulse, which means it's not continuous, first of all, and it's not derivative. So it doesn't have derivative here, right? It's discontinuous, and you cannot compute the derivative as the half 0.5. But all those summations of sine and cosine, so the sinusoidal waves, they are continuous and they are actually smooth, which means it's not only like continuous, you can also have compute the derivative at any place. any place here using these sinusoids. So which means in this case, when you're adding up infinite numbers of continuous functions, you can finally get something discontinuous. So this is where this limit kind of counterintuitive of human beings, right? So I hope you can understand this concept at least, because you can try so imagine you have 100 continuous things, you add them together, it's definitely continuous, right? But the discontinuity happens, but when you add in them like infinite numbers of continuous things, finally it's possible to get something discontinuous, and you cannot, compute the derivatives. But this only happens when you have infinite. On computer, it's impossible to do that. So computer is not able to deal with things continuous and things of infinite numbers, right? It's always finite and discrete. Therefore, when we use this computer additive synthesis or simulation, you can never reach a perfect square wave, okay, by this type of formula. Using additive synthesis is never impossible, to recreate a perfect square wave using a computer. We will try this by ourselves later on, and you'll see this effect, okay, in pure data. But maybe let me continue with this video. Let's see what the author is trying to talk about.
That I'm sweeping under the rug here. Does the fact that we're forced into a certain value for the step function at the point of discontinuity make any difference for the heat flow problem? For that matter, what does it really mean to solve a PDE with a discontinuous initial condition? Can we be sure that the limit of solutions to the heat equation is also a solution? And can we be sure that all functions actually have a Fourier series like this? If not, when not? These are exactly the kind of questions which real analysis is built to answer, but it falls a bit deeper in the weeds.
Yeah, so for all those questions, it's very, very complicated. So if you are from the math major, or if you're interested, you can just read the real analysis, or there's also something called Fourier analysis. So Fourier analysis is actually like functional analysis. So it's talk about functionals. That's why it's actually a very deep topic to talk about here, but what I want you to have is some intuitive understanding of this concept that will be really helpful for you to understand everything, okay? And for functional analysis, we also talk about a little bit, very shallow of, how do you do this functional basis change for this Fourier transform, but everything is very intuitive in this class, okay? We are not talking about all those details, the questions about taking the limit and do this analysis and prove whatever.
Weeds than I'd like to go here, so I'll relegate that all to links in the video's description. The upshot is that when you take the heat equation solutions associated with these cosine waves, and you add them all up, all infinitely many of them, you do get an exact solution describing how the step function will evolve over time. And if you had done this in 1822, you would have become immortal for doing so. The key challenge in all of this, of course, is to find these coefficients.
The former president is a threat to our most fundamental freedoms. He has openly said he is proud.
So far, we've been thinking about functions with real number outputs, but for the computations, I'd like to show you something more general than what Fourier originally did, applying to functions whose output can be any complex number in the 2D plane, which...
Okay, so the next part is actually about the complex numbers, or if you think deeper, it's complex analysis. We will talk about complex numbers also later on, but let's stop here for this part. And before we get into the deeper concept of Fourier transform, let's continue with this, okay? Harmonic waves. So now I believe you have better understanding of what is additive synthesis, how do you create those harmonic waves using, adding up infinite numbers of sinusoidal waves of upper harmonics to create those patterns. So what we can do actually in pure data, because I introduced pure data last time a little bit. So what we can do here is that actually in pure data, there is some function which exactly helps you to do such computation. So what is this? Maybe, let me see. If you let me do this live coding again, because I think this will help you to understand this better. So let me put a graph here. Let's call it add with. Okay. And we don't give size here. So this is another table we can visualize. Okay. So in pure data, there is a shortcut. So if you don't use this shortcut here, what you will do is that you just create many different oscillators and you add them together. Okay, you just add those different oscillators together like this. For example, we have 440 here, then its upper harmonic would be 880, and you just adding them together. You can see that here. You can basically hear this. But we are using this shortcut, which is called cosine sum or sine sum. Okay. So, okay, maybe I should. Okay, I'm not going to live coding now. It takes too much time. I mean, I want to show you some ideas here. Let me delete this first and change it to okay. So if you use this cosine sum, this 1, 0 to 4 is how many numbers are there in this table. So if you go to property here, the property, you can see the size is 1.27. So it's like, a little bit more than this because there are some, DC and yeah, some nuances here, but it's just a little bit larger. So we can actually change this number to anything you want. Maybe double this, and then if we click this, if you go to property, you can see the size changed. Okay, it's this size plus 3. This is the size, and you can also change this to some number like smaller. So you can see this, right? This wave becomes less continuous. This property gives you this size. So this actually determines like how many numbers or the resolution of this table. How many numbers are there? How many samples are there in this table? Okay. Okay. So now you can see if we use smaller number, it becomes more discrete. We can also use 62 or 64. Right, and it becomes more discontinuous. I think a thing that you may wonder is that why we choose these specific numbers. Everything you see in this, digital signal processing is something like 64, 1024. I think, yeah, I'm not going to get into details, but I want to give you a hint. If you really do this audio setting, or maybe at some point in your life, you are going to deal with audios, all those numbers are like this, okay? So why people always choose these numbers? Why they don't choose something like 400, right? It's much easier, or 1000, right? It's just easier to read, easier to use. Why people use these kind of specific numbers? The reason is that actually all those numbers we use here they are of 2 of power of something. Okay, 2 of power of something, of some integer actually. So this is 2 of power of what? Of 6, right? This is 2 of power of 7, 2 power of 8, 2 power of 10, 2 power of 11, right? So we always choose the number of the multiples of 2. And also like why people will ask like why we always choose some number of this format. So one one reason why you might come up with one assumption is that because we are using computers, right? We're using this binary encoding 0 and 1. Therefore, when we talk about bit depth, right? Quantization, everything is up to a power of something. To a power 16 is 16 bits. To a power 32 is 32 bits. But actually, it's not. It's more than that. The real reason why we are using numbers of this format is actually illustrated in a video here. Okay. We don't have time to get into the details. We're not going to talk about this video, but if you're interested in this, you can watch it by yourself. It is explained here in this one. Okay, the fast Fourier transform, FFT. So we'll talk about Fourier transform. So this is an algorithm called fast Fourier transform.
Hey,
okay, so this fast Fourier transform,
with Priceline VIP Family,
actually,
you can unlock deals 5 times
deploys,
faster. You don't even have to be an actual family.
Polynomials of half the original set of endpoints is a property of y divided by a matrix notation, which means we have to multiply the value representation by the interpolation.
The computation.
We copy the domain
Then
or
this algorithm.
Let
like,
two of our initial points are 1 and -1, which at the next level of recursion means that x1 squared.
I use all these computation standards libraries computations for Fourier transform because it's fast. It reduces your complexity from exponential to log. N log n, yeah, something like that.
And negative x1 squared also have to be 1 and -1 respectively. And at the bottom layer, we have only one point, which ends up being.
We are using the numbers 2 of the power of something. Okay, so this is actually use this kind of structure. I would say if you're interested in algorithm, you can look into this. It's a very fascinating algorithm. It's widely used by everyone, and it's very famous. It's like the real human intelligence of how people designing algorithm, how people save the computation and do the Fourier transform really fast. But this gives you a hint that why we are using these kind of numbers, right? These kind of numbers that's 2 of power something. So here we are actually using this cosine sum, and this something called sine sum. So sine sum is a sine function, cosine sum is a cosine function. And let me change this back to 1024. Okay. So sine sum, cosine sum. So why it's called sine sum and cosine sum, which means sum sine waves together, right? It's used additive synthesis. So here, okay. So here, actually, I created the functions to create square waves, sawtooth, and triangle waves. So what this function sine sum does is that this actually gives you how many numbers are there, how many samples are there, and this one is the amplitude for the first first harmonic, and this is for the second harmonic, third, fourth, fifth, and the function of computing square wave, actually you can find it here. Right? So this is a square wave. This is how you can compute those square waves. So for square waves, it's actually you adding up the odd harmonics only. Okay, there are only odd harmonics here. You can see this is 2k minus 1. Okay, 2k minus 1. So it's not k. It's 2k minus 1 means you only have the number of 1, 3, 5, 7, right? The odd numbers. So here you are adding the odd harmonics together, and the amplitude is given by 1 over n. So n is these numbers. So the first first harmonic is of amplitude 1. The third is 1/3. The fifth is 1/5, right? It's 1/n amplitude. And the phase is sine. So you are actually adding sine waves here. Okay. Therefore, how do we calculate this? Here is that we are using sine waves. And you can see all those odd harmonics here, or the even harmonics here are 0. Okay, so this 1, 2 is 0, 4 is 0, 6, 8. All the even harmonics are 0, and the odd harmonics are actually, this is 1. This is 1/3. This is 1/5. This is 1/7. This is 1/9. Okay, so this is the formula for getting the square wave using additive synthesis. So you can see here we get the first stage or preliminary stage of square wave, because we have too few harmonics. So we said to get a perfect square wave, you need to add them infinite numbers, right? Infinite numbers together to get a square wave using Fourier series. But here we only have 9 harmonics, which is like this. So what we can do is that we can see how this square wave is created. Okay. So let me do this. So let me delete everything here. Only the first harmonic. Okay, so this is a sine wave, pure sine wave. Now, let me add the first one. So this is 0, this is 1/3. Okay. When I add the 2 harmonics here, okay, you can see how the waves change. Okay, I'm adding the first and the third harmonic here. And now let me add the fifth one, the fifth harmonic. 0.2. And this is what I get. Okay. And let me add one more. Okay, so it's more and more like the square wave. It's approximating the square wave, right? Step by step. So the more harmonics I add, the better the shape is. So it's like this. So for sawtooth and triangle, it's of the same concept. Okay, the same concept means so we have the formula here for triangle wave. It's still you only adding up the old harmonics. It's the only difference between the square and triangle is that the amplitude is different. So amplitude for square wave is actually decreasing at n of power 2. Okay, it's decreasing much faster, and the wave we will use is cosine wave. So you can see when we talk about triangle waves, we're using cosine here, and for cosine wave we have some DC component. So yeah, so we start. This is the first harmonic here. Okay, this is first, the third, fifth, seventh, the ninth, and all the even harmonics are 0. And this is a triangle. So it's like inverted triangle. Okay. This is triangle wave. So similarly, we can do the same, right? We can do the same. Let's see how we get this triangle wave step by step. So this is the initial cosine wave. Maybe add one more harmonic. So you can see the amplitude is 0.111, right? It's much smaller than the sawtooth amplitude, because it's 1/3 square, right? So here is 1/3 square, and here is 1/25, right? And this is 1/49. This is 1/81, right? So it's much smaller than that. Let's see. Okay. So only by adding kind of two harmonics, you can already see the shape, right? It's like the triangle now. Maybe add one more, right? So it's approximating the triangle with something went wrong. Okay. So once I get the frequency, the amplitude wrong, you can see how the wave changes. So this is for a triangle wave, and for sawtooth, it's the same idea. So the sawtooth here, for sawtooth, actually all the harmonics are presented, even and odd. Okay, so you can see this 1, 2, 3, 4, 5. It's even and odd, all harmonics are presented, and amplitude is 1/n. Okay, and we're using sine waves. So if we go back here, you can see for sawtooth, we use sine sum, and all the harmonics are presented. And compare square and sawtooth. You can see all the harmonics are the same, right? The number are the same. It's only we are replacing all those zeros with our harmonics, even harmonics. And this is sawtooth we get. Okay, it's approximating the sawtooth wave, right? Like this. So we are not going to do. So it's the same idea. Okay, and here actually we can listen to this wave table. Let me see. Okay. Okay, so this is the sawtooth. Okay, so this is tab read, which means it's reading this wave table, this wave A table. Okay, and this is a device I just wrote to read this table. This is sawtooth, about triangle, square. Well, it doesn't work. Something is wrong. Phasor. Okay, so yeah, seems something go wrong here. Okay. Let me try it again. Okay, and if it doesn't work, it doesn't matter. It's not significant. Okay, so I guess something probably went wrong here. I cannot really listen to this table like well, but yeah, at least this function works. So you know how you use additive synthesis to get those tables. Okay. I see. So actually the sampling rate is wrong. Yeah, I should change this number to 400. Okay. Then I can listen to this. Okay, so this is yeah, I need to change the table to the same kind of scale as this device, this audio playing device. But whatever, it's not important. for our concern. Because actually we can listen to these waves better here in this Audacity. Okay. Okay. So we talk about additive synthesis. The next step will be talking about Fourier transform in more details. But before that, let me address your homework. Okay, your assignment 4. Because in your assignment 4, let me open this. So we already talked about the first 3 points in our previous lecture. And I'll also briefly address the square waves with and without aliases. So here, since we get into more details about additive synthesis, I think we have a better understanding now about what is square alias, what is square without alias. So for this square wave, okay, this square with alias, which means the square wave here is perfect square waves. Okay, so it doesn't use additive synthesis here. Actually, I believe it's just creating positive and negative numbers and just play them through the speaker. Okay, that's why it creates alias, because when you think about perfect square wave, then in terms of sinusoids, you're adding up infinite upper harmonics, right? And when we talk about Nyquist limit and the alias last week, so everything, any frequency above half of the sampling rate, right? They will be fold over, and this will create the alias in our listening. So therefore, when you have this perfect square wave, it actually has infinite upper harmonics, which means it exceeds the half of sampling rate, and then all the frequencies, they just interfere with each other when they fold over. And this creates something not that consonant. And there is another function in Audacity. It's called square alias. Okay. Let me rename this track. Square no alias. Okay. So let's see what this will create. Generate tune, no alias, generate. Okay. So you can see this square wave here, right? When you generate the square without alias, it's not the perfect square anymore. So you have this nuance. Even from here, you can tell it's not, there's some ramp, some slope here. It's not like, immediate change here. So you can see in this perfect square wave, it's just strict, minus, plus, positive, negative in here. But in this square without alias, in this conjunction, there are some continuous, right? Continuous kind of processing, continuous things here that makes the wave, smoother and more, I don't know how to describe this, but maybe we can listen to this square. We're going to do a comparative listening here and see. Okay, so this square without alias. I don't know if it's clear or not. Right, so this square wave is actually much brighter, much harsh, in terms of listening. Okay, so maybe it will, I don't know. Yeah, I hope this example should don't know how much frequency will be obvious. But here, this alias, yeah, maybe I should change this to some other frequency, because maybe 6622 is too large frequency that you cannot perceive that. Okay, let me try this. Let me try 400. Okay, it's a lower amplitude, and then about this one. And actually, you can just experiment by yourself, okay, with different functions, different frequencies, and maybe you can find a better kind of sighting than I do. Fair noise. Okay. Maybe this is better because I set the fundamental frequency lower so that if it's harsh, it's more like obvious. Because if the original tone is already very high, already very bright, then maybe it's not that easy to observe this effect. Yeah, I'm not very sure if it's really the case, but okay. So again, even if we change the frequency, yeah, the basic setting is the same. For square without alias, it's more smooth. It has some transition part here, but for the perfect square, it doesn't have transition. So square without alias, it actually means it in this square wave, it eliminates all the frequencies above half of the sampling rate. So our sampling rate here is the standard, right? 44100. It's the standard rate. So which means in this function, it eliminates all the upper harmonics above 22050, right? Half of the sampling rate, and which actually now creates a square wave without the upper frequencies folding over, which eliminates the Nyquist limit. Okay, maybe let me try this again. Let me play this again. So this is kind of dissonant, because if you think about square wave or any harmonic wave, it should be periodic, right? All the frequencies here are upper harmonics of each other, therefore it should be consonant if you use this musical term, because there's no like tritone or nothing, no harmonics that's conflicting with each other. But here in this tune, although it's square wave, it sounds like something very like has artifacts, very harsh. This is because the frequency, when the frequency is folding over, and then it's no longer like harmonic, with the previous harmonies. What I mean is that, okay, right? So this is the frequency, and this is the fs over 2. And for here, you have, right? This is your basic frequency, and these are the upper harmonics. You can see they are of the same intervals, right? Always of the same intervals here. And this will just, because you're adding like infinite numbers of sinusoids, so this will extend to infinity. So now, when we use this no alias function, we don't have everything here. Okay, we only have the harmonics here. That's why what we hear are the consonant part of the upper harmonics of one fundamental tone. But if we continue with the square wave without with all the harmonics presented, then when we are doing this sampling, these frequencies will fold over. Okay. How they fold over? This actually is a reflection. Okay, it's a reflection, which means okay. So fx here. Let me find a better color. Maybe this one. When it reflects, it will be here. Okay, so the frequency will be here. This frequency will be here, and this frequency, you know, is when it reflects, maybe here. Then what you are hearing is a combination of tone of the fundamental frequency in red and also this folding over, you know, these aliases of this magenta color. And these frequencies folded over, they don't form the harmonic series with the original tune. So this is your fundamental frequency. Okay. So these folded over frequencies, they don't belong to the harmonic series of your fundamental tune, which actually creates this dissonance here. Okay, it's not harmonic anymore. This is the reason why when we listen to this perfect square wave, it creates, you know, this dissonant kind of perception. But when we play this one, right, it only contains the harmonic series of the fundamental frequency. Right, so this one is with much less artifacts. Okay, so this is what I want to illustrate about this, the last part of aliasing. I promise we're not going to talk about aliasing anymore. This is the last part. And okay, so in our next next lecture, next part after break, I will talk about the effects in Audacity. Okay, so because your homework, the last part is record a piece of audio and experiment with various effects in Audacity. So these are actually much easier concepts than what we're talking about. Is less theoretical and less, you know, research oriented. It's more like about sound production, audio kind of processing, some things, but they are really like interesting things, interesting effects. So I want to introduce some of them to you so that you can experiment with them and maybe create some, you know, interesting sound effects, some maybe even you know, write some music and, you know, adding those different effects and just have fun with the Audacity. Okay, so this is what we will do after the break. So okay, so let's have a 15-minute break. Let's get back at 3:50. Okay, 3:50. Okay. See you.